Welcome to the first video on solving exponential and logarithmic equations. In this video we'll look at the simplest method of solving exponential and logarithmic equations, which is solving by using the one-to-one property of the exponential and logarithmic functions. Now we know that the log is the inverse of the exponential and the exponential is the inverse of the log, and we also know that only one-to-one functions have inverses. So the exponential function and the log function are both one-to-one functions, and we say a function is called one-to-one when for any number a, b in the domain of f, if a is equal to b, then f of a is equal to f of b, or if f of a is equal to f of b, then a is equal to b. Now, to see how to use this one-to-one property to solve exponential equations, let's look at the left, example 1. And it says here 4 to the 2x plus c is equal to 4 to the x minus 1. So we have two exponential functions with the same base 4 equal to each other. And since f of a is equal to f of b, that means the a, the 2x plus 3, has to equal the b, x minus 1. So we start off 2x plus 3 is equal to x minus 1. We subtract x from both sides. X plus 3 is equal to negative 1. We subtract 3 from both sides. X equals negative 4. Since the domain of the exponential is all numbers, there's nothing wrong with negative 4 being an answer, so the solution is x equals negative 4. Now, as we said, the logarithm is also a one-to-one function, so we can use that same idea. Example 1 on the right says to solve log 5 of 2x is equal to log 5 of x plus 1. Now, it's important if you're going to use this principle that they be the same log base on both sides. Just like in the first example, we had the same exponential base on both sides, the base 4. Here we have the log base 5 on both sides. The left is f of a, the right is f of b, where a is 2x and b is x plus 1. So since f of a equals f of b, then a, the 2x, is equal to the b, x plus 1. Moving the x to the other side, we get x equals 1. Now, unlike the exponential function, the log function is not defined for all x, so we have to be careful when we come up with a solution to make sure that that solution is in the domain of the log. Recall that the log graph looks like this. And note that it's not defined for any negative values of x, no values of the log over here, which means that if we come up with a negative answer, or even if we come up with 0 for an answer, note too the logarithm never quite makes it to the y-axis. So if we get a number for our answer, which causes us in the original equation, that's up here, causes us in the original equation to be taking the log of a negative number, then we have to throw that out. Well, if I put x into the first argument of the log, I'm taking the log 5 of 2. That's fine. That's not a negative number, and it's not 0. If I put a 1 into the second log, it's again log 5 of 2. That shows, for one thing, that the two are equal, so this is a solution, and it is in the domain of logs, so that answer checks out, and we give the answer x equals 1. Had that answer been negative 1, then on the left we would have been trying to take the log of negative 2. That would be undefined. We'd have to scratch our answer out and say no solution. But x equal 1 worked fine, so that's a good one. We've checked it. Let's go on to the next example. In the next example, when we first come to example 2 on the left, it looks like we can't use the one-to-one property because the exponential bases are different. However, you need to become familiar with numbers that are powers of other numbers, and 8 is a power of 2, namely 8 is 2 cubed. So what we can do is we can just change the 8 to 2 cubed. So instead of writing 8 to the 3x plus 5, I write 2 cubed to the 3x plus 5. And we have a rule that says if you have an exponential, x to the a, and you raise it to the power b, you get x to the ab. Well, that's what we have here. We have the exponential 2 cubed raised to the power 3x plus 5. So this is 2 to the 9x plus 15 is equal to 2 to the 2x. And now we do have the same exponential base on both sides, so now we can use the one-to-one property. So the one-to-one property says if f of 9x plus 15 is equal to f of 2x, then 9x plus 15 has to be equal to the 2x, which tells us that 7x equals negative 15, x equals negative 15 sevenths. Had I been solving an exponential equation, a logarithmic equation, I'd really want to check this answer out. But remember, the exponential function graphs like this. So its domain is negative infinity to infinity. There's absolutely nothing wrong with x equals negative 15 sevenths, so that's a good solution. Let's go to the second example too on the other side. Here, we're not showing a log base, so we're wondering, well, don't you need the same log base in order to use the one-to-one property? And yes, you do. However, when no base is shown, the base is 10. So both of those are logs base 10, and we can use the one-to-one property. So here we have 2x plus 3 is equal to x. We move the x over to the left and the 3 over to the right, and we get x equals negative 3. But again, this is the log function. It's not defined for all x. It's not defined for x equals 0. It's not defined for any negative x. And notice on the right side, we are actually taking log of x. So immediately this is thrown out. But even on the right side, if I plug the negative 3 into 2x plus 3, I'm trying to take the log of negative 3. That's also not allowed. We throw the answer out and we say no solution. So here's some examples of how you use the one-to-one property to solve exponential and logarithmic equations. But we're very limited. In both cases, we had to have either one exponential on each side, or we had to have exactly one log on each side. Otherwise, this technique could not be used. In the next video, we'll show some more general techniques.